Guys, let's take a look at this Cambridge University entrance examination problem. So we have here 9 multiply the x root of 4 plus 8 multiply the x root of 9 equals 22 multiply the x root of 6. What we shall do is to write these radicals in their exponent form. So let's get at it. So I'm going to be having 9 multiply 4 to the 1 on x plus 8 multiply 9 to the 1 on x equals 22 multiply 6 to the 1 on x. Now, 4 is 2 squared. 9 is 3 squared. Then 6 is 2 multiply 3. So I can rewrite this problem to be 9 multiply 2 squared raised to the 1 on x plus 8 multiply 3 squared raised to the 1 on x equals 22 multiply 2 times 3 raised to the 1 on x. Then I'm going to use this property of exponents. If I have a raised to the power of b, all raised to the power of c. So this is a power rule problem. When a power is raised to another power, we multiply the powers. But I can switch the exponents of the powers. I can write this to be a to the power of c whole power b. Just a change in commutation. So with this, I can rewrite this left-hand side to become 9 multiply 2 to the 1 on x all squared, then 8 multiply 3 to the 1 on x all squared equal to, then on the right-hand side, I will use what we call the product power rule. If I have two numbers, say a multiply b raised to the power of, say, y, I can distribute this power y between a and b to be a raised to the power of y multiply b raised to the power of y. It's called the product power rule of exponents. So then, this right side, I will then write it as 22 multiply 2 to the power of 1 on x multiply 3 to the power of 1 on x. The next thing I shall do, I will choose to divide by 3 to the 1 on x all squared. So I will divide this one by 3 to the 1 on x all squared, divide the middle term, 3 to the 1 on x all squared equal to, okay, no need to equal to, let me just divide straight 3, okay, 3 to the 1 on x all squared. I think it's better this way. So this term is going to cancel out. Then for these guys here, I can actually use another property of exponent. If I have a squared divided by b squared, I can then write this to be a upon b whole squared. So with this, I can then rewrite this expression. 9 into 2 upon 3 to the 1 on x. I will then put a bracket all squared plus 8 equal to, if I come to the right side, 3 to the 1 on x will divide 1 of the 3's to the 1 on x on the denominator. So this one will cancel out. I will still be left with 3 to the 1 on x here. So I will then be having 22 into 2 all over 3 to the 1 on x. Then at this level, our homecoming is guaranteed. I can then say, let k equal to, I'm trying to check my borderline. I'm using an algebraic substitution. K equal to 2 upon 3 to the 1 on x. So if I make this substitution, I can then refine the context of this expression I have here. So I'm going to be having 9k squared, Okay, no, okay, 9k squared, 9k squared, 9k squared, because k is 2 upon 3 to the 1 on x. So if I put k here, I'll be having k squared multiply 9, which is 9k squared. Then the middle we'll be having plus 8. To the right side, we're going to be having 22k. So this is a quadratics. So I will rearrange it. Take everything to the left equal to 0. So 9k squared minus 22k plus 8 equal to 0. So 9 multiply 8, that will be 72. Two factors of 72 that we can multiply together to give 22, that should be 4 and 18. Because of the negative sign here, we are looking at negative 4 and negative 18. So I can write, in place of 22k, I will replace it with negative 18k and negative 4k. I will have 9k squared minus 18k minus 4k plus 8 equal to 0. So if I factorize by grouping, 9k squared and 18k, 9k is common. 9k divided 9k squared, that will be k. 9k divided 18k, that will be 2. Then here, 4 is common. 4 divided 4k, that will be k. 4 divided 8, we are going to have 2 there. So we now have 9k minus 4, k minus 2 equal to 0. I need not do this. This actually because of the sake of our audience who are still in high school. So we cannot have that 9k minus 4 equal to 0 or k minus 2 equal to 0 from the zero product property. So here we have 9k equal to 4 or k equal to 2. If I divide both sides by 9 here, I'll be having k equal to 4 upon 9 or k equal to 2. So we have done very well. Now, along the line, we made a substitution that k is 2 upon 3 raised to the 1 on x. So I will take off this part of the board. We are at the very last lap. So recall that k equals 2 upon 3 raised to the 1 on x. Now, when k equals 4 upon 9, I can then write 2 upon 3 raised to the 1 on x equal to 4 upon 9. And 4 is 2 squared. 9 is 3 squared. I can also write this to be 2 upon 3 all squared. So if we have 2 upon 3 to the 1 on x equal to 2 upon 3 all squared, we can see that the bases are the same. It means that the exponents are equal. So this implies that 1 on x equal to 2. That also implies that if I take the inverse on both sides, s equal to 1 on 2. Then, for the second case, when k is equal to 2, so when k is equal to 2, we are then going to be having 2 upon 3 raised to the 1 on x equal to 2. So here, the bases are not the same. It means that I should log both sides. Moreover, okay, take the natural log of both sides or take the common logarithm on both sides. I think I will take the natural logarithm. So I will say, okay, ln of the argument 2 upon 3 raised to the 1 on x is equal to ln of 2. Then, according to the power rule of logarithm, if the argument of a logarithm is raised to an exponent, the exponent will come to the back. I'm going to be having 1 upon x ln of 2 upon 3 equal to ln of 2. Now again, when the argument of a logarithm is dividing each other, we use the division slash subtraction rule. So I can write this to be 1 upon x ln of 2 minus ln of 3, which is equal to ln of 2. Then, if I divide both sides by ln of 3 minus ln of 2 minus ln of 3, I'll be having 1 upon x equal to ln of 2 divided by ln of 2 minus ln of 3. Because I have the inverse of x here, if I take the inverse on both sides, I'll be having s equal to ln of 2 minus ln of 3 divided by ln of 2. So if I decide to clean this up, s will then be ln of 2 divided by ln of 2 minus ln of 3 divided by ln of 2. So it's actually going to give me x equal to ln of 2 can cancel each other. We have 1 minus ln of 3 divided by ln of 2. So guys, we have two values for x equal to half, then s equal to 1 minus ln of 3 upon ln of 2. Now, because of time, if we actually plug this into the original equation, we are going to have an approximate value. This is actually the exact solution. So guys, we've come to the end of another interesting tutorial. Please give this video a like, ensure you share to learned friends and colleagues, and most importantly, make sure you subscribe and turn on the post notification. See you next time.